New proof of the Pythagorean theorem. Y'all, this is super exciting. Even today, math is happening all around us. Not only is it exciting to see a new proof of the Pythagorean theorem, it was two high school students from New Orleans, Kelsey Johnson and Nakia Jackson, who proved the Pythagorean theorem using mostly trigonometry and then presented those findings at a regional conference for the American Mathematical Society. I was not proving mathematical theorems in high school, so very impressive, ladies. Well done. The students came up with this awesome shape that they call the waffle cone. And you know I had to do it. I threw it into Desmos. That's what I've got here. The waffle cone, along with your basic definition for the sine ratio and then something called the law of sines, is what they used to prove the Pythagorean theorem. And this is pretty impressive because up until a little over a decade ago, it wasn't really thought that you could use trigonometry to prove the Pythagorean theorem. This is because of a fundamental identity in trigonometry: sine squared x plus cosine squared x equals 1. We actually give this the name the Pythagorean identity. For a long time, it was thought pretty much any trigonometrical attempt to prove the Pythagorean theorem would implicitly rely on this Pythagorean identity, and that's a problem because, as you might imagine from the name, the Pythagorean identity comes from Pythagorean theorem. And so the idea was pretty much any trigonometric proof of the Pythagorean theorem would implicitly be circular. The students avoided this by using the law of sines and, again, the basic sine ratio, neither of which depend on the Pythagorean identity at all. Now, it's also true that they had to throw in some calculus there. They ended up using a couple infinite series to make their proof work, but I think that's just all the better. The basic idea behind the proof is this. We're aiming for this statement: a squared plus b squared equals this special ratio 2ab over sine 2 alpha equals c squared. So obviously you can tell without that intermediate step, you've got the Pythagorean theorem. The students start with just your basic right triangle, side lengths a and b, hypotenuse length c, and then across from those side lengths we've got angles measuring alpha and beta. We can say right away things like sine of alpha equals a over c. And again, this just comes from your basic definition for the sine ratio, the length of the opposite leg from a certain angle divided by the length of the hypotenuse. This would also mean we could say things like sine of beta is equal to b over c, which is what we use in the next step. That next step involves getting a 2 alpha involved. Now you can see this original right triangle doesn't have any angle of 2 alpha, and so the students very cleverly reflected that standard right triangle over and got us an isosceles triangle instead. The isosceles triangle has vertex angle 2 alpha, that's the one that we're going to need for this ratio down here, and then base angles beta and beta across from the lengths that were our hypotenuse in the right triangle a moment ago. Using something now called the law of sines, we can say that sine of 2 alpha over 2a, that is the side length across from that vertex angle of 2 alpha, is equal to sine of beta divided by c. But remember, we know what sine of beta is. We said by your basic definition of the sine ratio, sine beta equals b over c.
We can say that sine 2 alpha over 2a is equal to b over c squared. By multiplying both sides of that statement by 1 over b, and then by using the reciprocal identity, we get here 2ab over sine 2 alpha.
And so in fact we can engage in a little bit of substitution here, and alpha is equal to c squared. Now the next couple steps get quite a bit more complicated, and they involve the waffle cone shape, these kinds of infinite series of similar right triangles, and then a literal infinite series that we use to compute the values u and v. But the important thing to recognize is fundamentally this is still just a basic sine ratio relationship. Sine of 2 alpha, this angle up here, is equal to the opposite side in this now larger right triangle from the waffle cone shape. That opposite side we could call u, divided by the hypotenuse of that waffle cone shape, which we could call v. Once we compute those infinite series, we can take that relationship, manipulate it similarly to what we did a second ago, and end up with this statement: a squared plus b squared equals 2ab over sine 2 alpha. With that, we have everything we need to say, yes, for sure, Pythagorean theorem is on solid ground. Again, just a fantastic job by Kelsey Johnson and Nakia Jackson. Very cool result. The Pythagorean theorem proven using not only